I'm Shigeki Inoue now. I'm working in South Korea, but I will move to Hebrew University of Jerusalem this December. Today I will be talking about disk formation and bulge formation in clump-cluster galaxies. So many people have already talked about clump-cluster galaxies. I can quickly go through my introduction. So the most important thing is that these clump clusters and chain galaxies are thought to be infinite disk galaxies in their formative stage. For example, clump clusters are galaxies seeing Edgeon and Phaeton, and these are seeing Edgeon. And this is the first numerical simulation of demonstration of clump cluster this galaxy formation through clump cluster by Noguchi 98 and 99. So this simulation has indicated that initial disk is very high gas rich, and dynamic instability gives rise to these giant clumps, and the giant clumps merge with each other, and the main form a central bulge at last. Okay, and then some simulations has performed in a cosmological context and indicate similar results. Okay, but I still cannot conclude that, for example, nearby spiral galaxies are evolved from these high redshift clump clusters, because these clump clusters in current observations, the majority of them are too massive to evolve into Milky Way sized galaxies, and because the clumpy disk phase may not be a common stage of this galaxy formation. This means that some galaxies may prefer quiet formation process without violent disk instability. So my problem is whether for example, our galaxy was once a clump cluster, and nearby these galaxies were once clump clusters. So, and I performed a numerical simulation with SPH called Ashura, developed by Saito-san, and I used the isolated galaxy model. My simulation assumes NFW model, spherical NFW model with this mass, and the 6% of the mass is assumed to be primordial gas, but the gas sphere has rotation like this, and I start the simulation. And the gas collapses into the central galaxy, and they form clumps, and finally evolves into this galaxy. Okay, please let me show you my simulation. We are now looking at the galaxy from face-on view. Many clumps are forming in the disk region, and they are pouring into the center by dynamic friction. And the star formation is concentrated in the clump region. And these are pouring into the center by dynamic friction, and finally form a massive bulge at the galactic center. Like this final one's a bit long-lived. Yeah. Anyway, my simulation is like that. And this is the overview of my simulation. This phase corresponds to this clump cluster and this chain galaxy. And finally evolves into these galaxies with bulge. And nearly 10% of gas remains in the disk region. And disk follows an exponential density profile with a scale radius of nearly 4 kiloparsec, and a bit larger than the Milky Way, but very similar. And the bulge to total mass ratio is 0.37. Okay, let me talk about the bulge formation in my simulation. Today's talk, I call the bulge in my simulation clump-origin bulge. So the galactic bulge are generally classified into two types: classical bulge or pseudo-bulges. Classical bulges are thought to be made by galactic merger. On the other hand, pseudo-bulges are thought to be made by secure evolution, for example, by spiral arms or bar structure, something like that. And the clump clusters follows the Walk-Rule profile, and the pseudo-bulges follow exponential profile. And the clump cluster, classical bulge is generally old, and the pseudo-bulge is relatively young. But clump-origin bulge is not made by galactic merger or secular evolution, so we cannot classify. So we cannot the clump-origin bulge. We cannot classify the clump-origin bulge into or classical bulge or pseudo-bulge. So my problem is which type is the clump-origin bulge classified to? So the self-profile fitting is known to be a good and simple diagnosis to classify the bulge type. So this is the fitting profile. The red line is the simulation result that I fit with self-index bulge, self-profile bulge, and the exponential disk. So I found that this bulge has the self-index of 1.02. This means that the bulge profile is almost exponential. This means this is this one of the pseudo-bulge signature. So my simulation has indicated that the bulge is looks like pseudo-bulge. And this is the bulge shape. We are now looking at the bulge face on and the edge on. So I think you can see our boxy shape here. The boxy shape is a signature of pseudo-bulge. And this is the rotation B over line of sight velocity over sigma 0. And I can find significant rotation in the bulge. So bulge is rotating. This is also pseudo-bulge signature. So I can say that clump-origin bulge is similar to pseudo-bulge in dynamical property. Nearly exponential density profile and boxy shape and significant rotation. Okay, what's about the age, stellar population? So, I'm now showing formation time of stars as a function of galactic radius, radial distance. So, the disk region is younger than by 0.5 giga-year or something like that than bulge. So, I can say that the difference is very, very small. I can say that the bulge is almost coeval with the disk. But the disk structure is formed in high redshift galaxies. High redshift. So I can say that the clump-origin bulge is old structure. Okay, next. The metallicity. I'm showing metallicity distribution. The bulge is more metal-rich than the disk region. So I can say that the bulge is metal-rich bulge. So to summarize my bulge property, clump-origin bulge. So my clump-origin bulge looks like pseudo-bulge in dynamical property, but the stellar population is like classical bulge, old and metal-rich bulge. So I can say that clump-origin bulge is neither a classical bulge nor pseudo-bulge. So it's very interesting to compare with the Milky Way bulge. Milky Way bulge is supposed to be pseudo-bulge because the bulge galactic bulge has exponential profile and oblate shape and someone may say X shape and significant rotation. But still, population is like a classical bulge. The galactic bulge is old stars, composed of old stars, and high metallicity is also observed in the bulge stars, galactic bulge stars. So I can say that clump-origin bulge resemble the Milky Way bulge. So, but I have to notify that other results have shown that clump-origin bulge are like classical bulge, not like pseudo-bulge. But my simulation is different from these work in the point of initial condition and the methodology of the hydrodynamics. Okay, let's take a look at bulge. Next disk. Okay, I'm showing vertical density structure of my simulated galaxy here. So I can see less massive thin disk here and dominant thick disk here. So in my simulation, thin disk has hardly formed. So this is because thin disk formation needs rate gas accretion, but my simulation does not include rate gas accretion. If my accretion including if my simulation includes the rate accretion, thick disk will be much more dominant, I think. So many thick disk formation scenarios has been suggested. For example, one stellar accretion from dwarf galaxy and thin disk heated by dwarf galaxy, or radial migration by spiral and something like that, or multiple gas-rich merger. And recently, recently thick disk formation in clump clusters has also been suggested by Bono et al. 2009. And the clumps in clump cluster heat up the disk and supply stirs by the disrupted clumps. And the orbital eccentricity distribution is known to be a good proof of thick disk formation scenario. This is the observation of Milky Way. Milky Way thick disk stars. And this is the simulation, the results of simulations gathered by E et al. 2011. Scenario 1, 2, 3, 4, 1, 2, 3, 4 correspond to. 1 is stellar accretion from dwarf galaxy, 2 is thin disk heating, and 3 is radial migration, 4 is multiple gas-rich merger. So in this plot, scenario 1 seems to have too high average value, and scenario 2 has bimodal distribution. These are maybe inconsistent with the observation of the Milky Way thick disk, but number 3 and number 4 looks consistent with the real observation. So these two scenarios could be past this proof. So, but scenario 5, clump cluster is thick disk formation in clump clusters has not been discussed, and I discussed now. Okay, this is the result of my simulation eccentricity distribution of disk stars. The distribution is very similar to the observation in the Milky Way. So, okay, I put summary here. So, the bulge, in my simulation, bulge looks like pseudo-bulge in dynamical property, but the population is old and metal-rich. The clump-origin bulge is not classical bulge or pseudo-bulge, but the Milky Way bulge is very similar to my clump-origin bulge. And about thick disk, the orbital eccentricity distribution can be a proof of thick disk scenario, but I didn't find clear discrepancy from the Milky Way thick disk. I mean that clump cluster scenario cannot be discarded in my simulation. However, we have to notify that my simulation may be still insufficient in stellar feedback, so my feedback is still weak. My simulation may be suffering from overcooling problem because of the weak stellar feedback. Okay, thank you very much.
Okay, questions? Adisha.
You say the bulges are pseudo-bulges.
Yes.
I reported on several simulations, cosmological, in which the bulges are pretty classical.
Classical, yeah.
Now I can think of many mechanisms in cosmology that will thicken the bulge,
Yes.
make it wetter and so on. So I'm not surprised about this difference, but in Frederick Bernoulli's simulations, which are also isolated galaxies,
Yes.
they also find classical bulges. Did you think about what might be the difference? Changes in this classical bulge?
Yes. On the difference from the Green 2008, I think the cause maybe the difference of the methodology. They use the sticky particle method. Sticky particle method tends to become low gas fraction, something like that. And so I think the difference to be classical bulge or to be pseudo-bulge depends on gas fraction, I think.
What is the gas fraction in your case?
In my case, gas fraction, sorry, I cannot say now. Yeah. Anyway, so yeah, I try to use many other initial conditions, different spin parameter or different angular momentum distribution, something like that. But in my simulation, in all cases, my bulge was pseudo-like bulge-like.
Joe.
At the beginning of your talk, you said that the clumpy galaxies, or what you call the clump cluster galaxies, are more massive than the Milky Way. And I just wanted to emphasize that, as Inoue has also pointed out, that's certainly not a characterization of the Candle's observation. They're the galaxies that are more massive in stellar mass than about 10 to the 9.5.
Yes.
If their radius, their half-light radius, is larger than about 2 kiloparsecs, they're a high fraction of them are clumpy. If it's greater than 3 kiloparsecs, they're practically all clumpy if they're star clumpy. So it's true across a wide range of masses.
Yes.
And also a wide range of redshift.
Okay. Yes. Thank you very much.